interesting talk.
Hello.
Hello.
Hi, can you hear me?
We can.
Okay. So, just a brief introduction. This presentation, the title of which is an empirical validation of the computational unified field theory versus quantum and relativistic models. This presentation is following up an accepted paper or chapter to Intech's upcoming quantum mechanics book. I should just mention the fact that what I'm trying to present in this presentation is essentially the gist of the 4, now 5 previous articles describing this computational unified field theory as a candidate theory of everything. And specifically in this presentation, also a first, I believe, empirical validation of this theory. Okay. Okay, just the opening slide is what if Einstein was right. There's actually a book of mine with this title, essentially just highlighting, hinting or highlighting the fact that perhaps, I believe in this conference in general, Einstein and people like him that have been looking for unified field theory or theory of everything may have foreseen something that we're all now searching for. Okay, can we go to the figure 1, the next slide? Okay, the duality. So essentially, I just want to describe briefly the variation of this computational unified field theory, first of which is the duality principle. And essentially the idea behind the duality principle, that's actually a computational principle that I discovered in the field of neuroscience, and then it was applied towards this theory in physics. But this computational duality principle essentially says that when you have a system such as the quantum and relativistic systems that tend to have a specific computational structure, in a sense it essentially says that when you try to determine the values of a y factor just based on its interaction with another x factor, this leads to some problems computationally. It leads to logical inconsistency and computational indeterminacy. I'll just show it briefly in the case of quantum computational systems and relativistic systems. And essentially in both, there is, from a computational standpoint, there is a flaw, where there is a problem, which is in quantum systems, we're trying to determine the values of a subatomic target strictly and solely based on its direct or indirect interaction with the probe target. In relativistic systems, similar or the same computational structure, we're trying to determine a phenomenon value, which is space-time or energy mass values of a given object or event or phenomena, strictly based on the direct interaction of that phenomena with a differentially mobilized relativistic observer. And the problem is that in this, so I call this self-referential ontological computational system, SROCS. And the problem is that in the specific pieces in which this SROCS system actually measures, for example, I'll just give an example with the quantum system, before the collapse of the wave function, potentially the target obviously occupies a whole series of this probability wave function. So if we focus only on that, after the collapse of the wave function, only on the measured collapsed value, which I represent here as n. So for all those, look down where it shows the Strong's quantum or Strong's relativistic. In other words, in those, for all those values that are not the measure, the collapsed value in the case of the quantum system, we actually get a situation that in the same computational level, we have the uncollapsed values, which is all the spectrum of values, so not n, and the collapsed value, but after the collapse, it's only the not, all the values that were not measured essentially seem to both exist and not exist at the same computational level. which leads essentially to a logical inconsistency. I, of course, describe it in greater detail in the article, but in simple terms, this computational structure, which tries to determine the value of the target or the phenomena in relativistic systems, strictly based on its interaction with another entity, the probe or the relativistic observer, leads to a situation of logical inconsistency and then computational indeterminacy. And of course, we know empirically that both quantum and relativistic systems are able to determine the value of the subatomical target or of a specific phenomenon, and therefore the duality principle essentially proves that this structure, this computational assumed structure, that solely by the direct interaction you can determine whether the target has a certain value or the phenomena has a certain value or not, leads to these problems, and therefore the duality principle essentially proves or points at a higher ordered, what they call D2, capital D2 level, which is a higher ordered computation of the target, the observed. So in simple terms, the duality principle essentially has identified a computational flaw or a computational problematic structure underlying both quantum mechanics and relativity theory, and it points at the need for a higher ordered computational principle or system that can compute the co-occurrences, simultaneous co-occurrences of the target probe or observer phenomenon theory. You can go to the next slide, please. Essentially, by the way, a fuller in the article that I've actually gone into greater details, but this duality principle that I spoke about essentially points at the fact that you cannot have more than one such higher ordered computational principle. You cannot have, for example, one D2 for the relativistic system and another capital D2 for the quantum system. It eventually points at the existence of only one such higher ordered computational principle. So the second postulate of this theory is called the universal computational principle. These postulates, partially proven, partially assumed, but this universal computational principle actually arises from the duality principle, and what it says is that the computational anti-field theory assumes there is a singular universal computational principle that has computational dimensions. And I'll go in a second into a cinematic film metaphor, because there is some resemblances between this model and what we see in a film, in a cinematic film. But essentially there is three computational dimensions. One is framework, which essentially talks about whether we're looking at when this universal computational principle produces an extremely rapid series of what I call universal simultaneous computational frames, or USDS. These frames comprise all the spatial pixels in the universe at the minimal time point. The rate at which the universal computational principle produces this extremely rapid series of universal frames is assumed to be c² divided by Planck's constant. And essentially these three computational dimensions that you see are a measurement they're measurements of the degree of change between frames, or the lack of change between frames. Look at the table below. So essentially the idea is that this universal computational principle essentially computes whether for an object, so the method computes at an object, looking at changes or lack of changes in the object, or the same for frames, looking at the whole universal frames or segments of the frame. And the idea is that when we look at when this universal computational principle computes the consistent or inconsistent measures of an object or a frame, you get we obtain the four basic physical features. In other words, mass is, according to this theory, computation, the universal computational principles computation of the object consistent presentations across these universal frames. Time is the universal computational principles computation of inconsistent measures of that object across frames. And then for the frame dimension, when we look at the whole frame or we look at segments of the universal frame, and we look at the degree of consistency, those spatial pixels that appear the same across a series of frames produce the spatial measure or dimension of an object, and those spatial pixels change the object travels a certain a number of pixels across the frames, produces or yields the energy feature. And then, by the way, the locus is parallel to the relativistic dimension. In other words, the question is whether this universal computation principle computes these four physical features for combination from the perspective of the object, local, or from outside the object. Okay, we can go to the next slide. The next theoretical postulate of this theory is called computational invariance postulate, and essentially this is a little bit perhaps counterintuitive and also far-reaching. Essentially, it's somewhat similar to Occam's razor, and essentially it says if this theory is correct, and if indeed we have this universal computational principle that produces this extremely rapid series of universal frames. By the way, each universal frame is produced simultaneously, all spatial pixels in the universe comprising such a universal frame at a minimal time point are all produced simultaneously by this universal computational principle. But this computational invariance postulate essentially states that if, in fact, the universal computational principle produces this rapid series of frames, it changes between the frames, during the frames, which gives rise to the four physical features that as we've seen in the last slide of space-time, energy, and mass. So we can identify that the universal computational principle is in fact a computationally invariant principle because it exists both in between frames, solely in between the frames, and it also produces the frames and gives rise to the computation of the four physical features, which are considered secondary computational byproducts or features of this computationally invariant principle, whereas the four physical features, as I said, are computationally invariant. They only exist during the frames as a function of the universal computational principles computation of changes or lack of changes between the frames, but they only exist during the frames, do not exist in between the frames. And so an extension of Occam's razor principle, one may say, is that if we have one computationally invariant principle, which is this universal computational principle, existing both in between the frames and producing the frames, giving rise to the four physical features, whereas we have the computationally invariant physical features that exist only during the frame and are produced by this computationally invariant principle. This computational invariant postulate essentially says that we then have the attributes or regard the physical features as phenomenal rather relative to the real or the invariant computational universal computational principle. Okay, we can go to the next slide. Okay, this converges, and of course it's very hard to describe the whole theory in a short period of time, but I'm just giving the gist of it. The other postulate, another postulate of the computational unified field theory is the universal computational formula, and essentially it says, or it's a postulate that you can see the c squared divided by h is the rate at which this universal computational principle signified by the EQ. There is a small